Good day, I'm Dr. T and welcome to my office. So today I want to talk about Earth systems and our relationship with those with respect to obtaining the stuff we need. Because as a society we need energy, and I talked about that in the previous video, but we also need stuff. And the stuff we need needs to be made from something, and we're going to have to get that something from the Earth around us. And that's going to affect Earth systems. Now, previously I talked about a bunch of cycles. I talked about the water cycle, I talked about rock cycle, I even talked about the carbon cycle in my previous video on energy. In this video I want to talk about other cycles, specifically the nitrogen cycle. So we have a nitrogen cycle, but on top of that we also have other things, such as an iron cycle. Interestingly enough, iron is a biologically relevant material, and there are places, generally in the ocean, in which the ecosystem is very much limited by the availability of iron. As such, more iron would cause more growth. On that same lines, we could have the phosphorus cycle. Phosphorus is another essential nutrient. It usually is in the form of phosphate, so PO4 3-. And in this case, it is included in the phosphodiester backbone of DNA, as well as the phosphates in adenosine triphosphate, aka ATP. So nucleic acids need themselves some phosphate, and we need ourselves some nucleic acids. This is one of the key fertilizers that plants need from their environment, one of the plant's macronutrients. Now, with this particular cycle, we're going from the lithosphere into the biosphere and the hydrosphere. So we're transitioning from soil/rock to water and living systems. And it's a nice cycle. Of course, in our quest for fertilizer, we will modify this cycle. We can disrupt it somewhat. And because phosphorus is so important for ecological systems, adding way too much phosphorus to an ecological system can cause a massive growth of plants or algae if it's an aquatic system, which can also lead to a boom-bust system and thus damage the ecosystem by having a big spike and then a big die-off. The same can also be said for nitrogen, I should point, which I will get to here in a little bit. We also have an oxygen cycle of all things. But of course this makes sense because oxygen is in our atmosphere, but it's also in things like minerals, like carbonate or phosphate minerals, as well as it reacting to form carbon dioxide, which is then returned back to the atmosphere via photosynthesis. So we've got ourselves a few cycles. But I want to jump into the nitrogen cycle. This one's particularly interesting because our atmosphere is majority nitrogen. It is the dominant gas around our planet. However, that is elemental nitrogen. The two nitrogen atoms are hooked together by a very strong triple bond. It's strong enough that it takes a lot of energy in order to crack that thing, and generally it doesn't do that. Nitrogen is quite often used as kind of a poor man's noble gas. It's cheaper than argon, and so if you don't need the argon for highly not reactive, nitrogen is sometimes good enough for a lot of applications. This is a problem because we want the nitrogen in order to incorporate it into biological molecules. Think the bases for nucleic acids or the amino acids to build proteins with. Well, that's a bit of a problem because we can't really do that. So we need what we call fixed nitrogen. Fixed nitrogen is basically any biologically available source of nitrogen. This could be organic nitrogen, such as those found in amino acids or nucleic acids. It could also be nitrate or nitrites, nitrogen hooked up to some oxygens and typically an anion, as well as good old ammonia. So those are typically going to exist in the soil, and the plants can suck that up with their roots. Of course, there are bacteria that make their living by extracting energy from nitrogen compounds by turning it into elemental nitrogen. So some of this is leaving the system. We're going to have to take some from the atmosphere and put it back in. We've got a couple of routes to do so. One is lightning strikes. Lightning has a lot of energy, more than enough to crack open a nitrogen, and there's generally a lot of oxygen around too, so we can form nitrous oxides, which can then turn into nitrate and nitrites. Now, once in the ecosystem, the plant sucks it up in its roots, the plant eventually dies or is eaten. Decomposers then process the plant, or the dung, or the animal that had eaten the plant, and return it as organic nitrogen back into the soil. Likewise, animals do end up eating a lot of nitrogen in their diet, way more than they need. We have kidneys or other excretion organs to get rid of the nitrogen, and that can go in the environment as urea, an organic nitrogen compound, or ammonia, depending on what particular animal you are, as well as uric acid, another organic nitrogen compound. Now, we have a lot of bacteria getting nitrogen out of the soil. We're going to want to put some more nitrogen back in. And conveniently, there is a set of bacteria. Actually, it's usually labeled as a bacteria, but I'm quite certain they're archaea, not bacteria. But there is a group of nitrogen-fixing archaea that often will live symbiotically with some types of plants in root nodules. These archaea really actually prefer an anaerobic environment, so the root nodules will make a nice anaerobic home for these archaea, and the plant will pay them in sugars, and the archaea will return the favor in fixed nitrogen. Plants are going to be so soybeans, peanuts, and the like, as well as sweet potatoes, certain types of alfalfa, and other miscellaneous plants that happen to have these root nodules. Now, we humans have learned to exploit some of these. One, manure makes better plants, so we've learned to gather manure and put them on fields or put them with the plants in order to enhance crop yields. Basically, if you give the plants the nutrients they need, they grow up big and strong and give you the nutrients you need. We can see references to putting manure on plants going all the way back to the Gospels, where there's at least one comment of saying, put some dung on that tree and let's see if we can get some fruit on it later. Long before we knew that some plants had symbiotic relationship with microorganisms to produce fixed nitrogen, or even that nitrogen was a thing, we did know that leaving a field go fallow, and thereby letting some of those said plants grow in the field, and letting the lightning strike and some rain flush in a few nitrogen compounds, did improve soil. You can go all the way back to the Tanakh and see references to letting a field go fallow or giving it a Sabbath, a rest. By the Middle Ages, we got a little bit better idea of exactly what's going on with those plants. Nitrogen still wasn't discovered. We were still thinking, Aristotelian 5 elements, but we did realize that certain plants made the soil better, and thus began a process known as crop rotation. Basically, you've got certain nitrogen-fixing plants, you plant those in your field, and then you have other plants that are going to give you lots of nice nutrients, or your cash crop. Could also be something like cotton, which isn't eaten but used as a resource. You plant that, and it uses up a bunch of nitrogen, but then you replace the nitrogen the next year with a new batch of crops. Over here in North America, the indigenous peoples had a slightly different approach, and that was the Three Sisters. Instead of planting the beans one year, the grain the next year, and the squash a year after, let's just plant them all together. The eldest of sisters, the corn, would be planted. This is going to grow up, create a nice stalk for the beans, as well as lots of calories, because corn. And then a couple days, or actually more like a couple weeks later, you would plant the beans. Those will grow up the corn, and beans are legumes and have wonderful relationships with microorganisms, thus fixing nitrogen for the corn. And later come the youngest sister, the squash, a few weeks later, in which case this grows up, gives you more food, but also keeps the weeds down because it makes big leaves and kind of dominates the ground, so you don't get other random weeds growing up and becoming a problem. Now, things were going well. By the 19th century, we're doing the crop rotation thing. We've run into a couple problems, though. Crop rotation worked well under feudal systems where one person owned a bunch of land and had a bunch of people farm it for them, and so that if one field wasn't producing a lot of food, but another field was, that was fine. You just kind of averaged them out. Whereas if you have small tenant farmers where their entire livelihood is on that field's production that year, they can't really afford to have an off year to let the field rest or to plant a less profitable but nitrogen-fixing crop. In comes George Washington Carver. If you look at his research, a lot of it is very much a form of study, or a form of education for his students, I should say. But also he is doing a lot of work on trying to make nitrogen-fixing crops, sweet potatoes, soybeans, and peanuts, more profitable, so that on that year when you're doing that rotation, you at least make a bit more money than you would have already. Additionally, we are starting to import mineralized bird poop. Good old guano. Turns out in the Atahara Desert and then a series of islands off the coast of Chile, so we're talking South America here, there is a lot of nitrate-rich soil and or just mountains of bird poop. Very low rain to wash out the nitrates and, well, birds for centuries. So you were able to extract the bird poop, ship it off to Europe where it could be used as fertilizer. This actually made several South American countries fairly well off because of nitrate mines as well as the guano trade. Additional rules were made that if you're an American citizen and find an uninhabited, I hate to say I have to use air quotes here, but I have to use air quotes on the word uninhabited, mostly uninhabited by a group that has an army, an uninhabited island with lots of bird poop on it, you can get yourself an island. This is how we got Guam, I believe. So this is being used as fertilizer, but this has a couple of problems. One, you need to ship via boat a bunch of fertilizer from basically South America. Great if you're the United Kingdom, where you've got the biggest navy on the planet. Not so great if you're Germany, who has a rather small navy, and the only way to get to the rest of the planet is around England. And you're not necessarily friends with said England. Yeah, that was a bit of an issue. Additionally, we're kind of running out of bird poop. The South American countries are having an economic boom at this time. Great for them. Unfortunately, they're also having a bunch of internal squabbles. It was like a three-way Cold War going on down there at this time. So not so great. Would have been nice for peaceful approaches, but you know, that's what people do. But this creates a problem. We're limited on bird poop. It's a strategic national resource of bird poop. In comes a guy by the name of Fritz Haber. He works up a process with a chemical engineer by the name of Haber-Bosch to take nitrogen out of the atmosphere and form a synthetic nitrogen. It's rather extreme. I'll put it here. It's not going to fit here. It's going to be like over here. This process, you basically take natural gas and air, react it under high heat. You get syngas, which is basically carbon monoxide and hydrogen. You then take that, you react it with some nitrogen from the air, and you get ammonia. Ammonia is fixed nitrogen, so now you can use the ammonia to make fertilizer, or nitric acid to extract phosphates to make fertilizer, or nitric acid to make explosives, because it turns out nitrogen is actually incredibly important for the manufacturing of explosives, and that's actually kind of the real reason this whole process was done, because, once again, Germany, not in a great spot. They need explosives to fight wars. Yeah, Fritz Haber gets a Nobel Prize, and it was ultra controversial at the time. He's also the inventor of modern chemical warfare, so there's a reason it was controversial. Now, as humans, we then use this to modify our nitrogen cycle, and this is important for us. Roughly speaking, at this time, the early 20th century, we're being hit by the Malthusian trap, or we're on the verge of being hit by the Malthusian trap. Thomas Malthus was a Scottish economist. He's kind of like the beginning of economics. And he writes a text in which he outlines a problem. Populations tend to grow exponentially, where resources, if you're lucky, grow linearly. At a certain point, the population outstrips the resources, and bad things happen. And we were worried of that. The carrying supply of the Earth, basically how much crops can we grow on the planet to feed how many people, was starting to get awfully close to where we were at, and there were concerns of overpopulation and running out of food. But with fixed nitrogen, we're able to feed our plants plenty of nitrogen via synthetic nitrogen to the point where about half of the nitrogen we ingest comes from the Haber-Bosch process. This was also kick-started a little bit further by a guy by the name of Karl Borlaug, who then uses this ready abundance of nitrogen in order to make more productive crops, such as things like dwarf wheat, that boost and create the green revolution of the 1970s, more or less ending famine, at least for the time being. However, this excessive use of nitrogen, which allowed for plenty of food, does destabilize the nitrogen cycle, and as I mentioned earlier, if you dump a bunch of nutrients into a body of water, you tend to get a boom-bust ecosystem for the algae and like, which results in problems for said ecosystem. Now, when covering synthetic nitrogen, I mentioned it starts out with both methane and nitrogen from the air. Kind of makes sense, at least the nitrogen part does. The methane is used for its hydrogen in order to put the hydrogens on the nitrogen, as actually getting H2 is quite the pain to produce. It's usually produced from methane, as methane is much more readily available. Well, methane, as well as the nitrogen, would be what we call feedstocks. Feedstocks are the raw materials, the chemicals you put into a reaction in order to make stuff. So these are like several steps before the reactants. These are your primary reactants. What do you dig out or grow or whatnot? Historically, most of your feedstocks are going to be plant-based, as well as the occasional animal-based. But if you want to make something, if you want to say make some paint, and you need some chemicals, you're either going to dig it out of the ground, some kind of rock and grind it up, or maybe you'll take some oils to make the binder part of the paint. So you could take some walnut oil or whatnot and smoosh together your pigments and make your paint. Now, as chemistry becomes a thing, as technology improves, we start looking for other feedstocks to make all kinds of the cool new chemicals we're starting to make. Things like turpentine in the 19th century start getting large, and then we move on to coal. We can make coal tar by roasting coal, extracting off methane, and use that for illuminating gas, basically little gas burners. But then we have this rather toxic sludge worth of material that we can then extract other chemicals from, do other chemical processes, and make things like aniline dyes, such as mauveine, which is where the first synthetic dye comes from. Later on, we then move into petroleum products. Petroleum, you don't have to do quite as much processing. It's got all kinds of wonderful, neat, nifty molecules coming out of the ground. Classic one is going to be ethene, which is a carbon double bonded to another carbon, and each carbon's got a pair of hydrogens on it. And this is great for making things like plastics. You can stitch them together quite easily, modify them up a bit, and make all kinds of wonderful synthetic polymers. Later on, we start working with natural gas. Natural gas, mostly methane, is relatively cheap. We can easily modify that into syngas, as I mentioned earlier, which is reacting the natural gas with water in order to produce carbon monoxide, which itself is an incredibly reactive compound. Toxic, but those two things usually go together, that we can use to make a bunch of other things from that, as well as giving us some hydrogen. And there are other processes that we can send the natural gas through to make all kinds of wonderful, neat, nifty chemicals. The future, we don't know. Natural gas is quite cheap and should be abundant for quite some time. However, there is work moving into more renewable feedstocks, those that we grow in a field. So kind of back to the way it was, we're now using plants again. Quite often genetically modified things. Soybeans are quite popular, continuing the work of George Washington Carver. In this case, sometimes the normal soybean, sometimes a genetically modified soybean to make the specific molecules that we want to use as our feedstock. Now, this jumps into an idea called green chemistry, and this has been a growing push since the 1990s. I'll put like a graphic over here, but the idea here, there's 12 points. I'm not going to go into the 12 points of green chemistry. I'll let you look those up if you want, but they're generally rather technical, and even me as a chemist, I go, okay, what are you saying? Oh yeah, that makes sense. So the idea here is, what are your feedstocks, and are they renewable? Ideally, you would like to be able to grow more. We're going to run out of petroleum and coal and natural gas. The more we use, there's only so much out there. Although natural gas, you can do a bioreactor, and it is actually renewable, although not quite so easily. So are our feedstocks renewable? What about the starting materials? How much are we using? Are we doing a process that's inherently safe, or is it a particularly dangerous chemical process? Can we do so with less energy? The less energy we use, the less pollution we get. Also, can we use a process that doesn't impact the environment as much? How do we keep waste down? How do we make sure that every atom we put in there, or at least as many as we can, goes from the feedstock and becomes our product, and we're not just wasting random chemicals? Can we avoid weird solvents that are toxic we have to dispose of? The idea on this is that after several environmental impacts, including the Cuyahoga River fire, where the river caught fire, not like the boats on the river, but the fluid in the river caught fire. I'd say water, but water doesn't burn. This was not water. It burned. We realized we needed to do better when it came to respecting the environment around us. because the environment around us also includes our neighbors. And so fish, yes, but also people. And the Cuyahoga River was not good to the people around it. So we needed to clean that up, which we did. But all this effort cleaning up the mess, we realized that maybe, just maybe, it would be a whole lot easier to not make the mess in the first place. And this is the idea behind green chemistry. Don't make the mess to start with, and also work with a system that's just safer. Remember the hierarchy of controls from many videos ago, where the idea of you either eliminate or you substitute? Let's try and substitute out. Let's just do inherently safer chemistry. Now, when it comes to feedstocks, quite often we're talking about that in, say, the chemical world. But that goes beyond just petroleum products making plastics. Feedstocks for metals are called ores. Ores are going to be minerals. They have hopefully a good amount of the metal of interest, and we are going to extract the metal in a process known as smelting. Basically, we've got almost certainly the cation of the metal. We're going to have to pump in a bunch of electrons. We've got a couple of ways of doing that. In the case of iron smelting, we mix the metal with coke. Coke is a purified form of coal or petroleum. Basically, you bake it, do pyrolysis to it, and that burns off the impurities, but you do so in a low oxygen environment, so it doesn't just burn. And now you're left with a very pure carbon. You mix that with air and iron, as well as some limestone, in order to help remove the impurities. And that all goes in, ridiculously high temperature. Out comes slag, which is the impurities, and liquid iron, which can then be processed into steel or whatnot. Aluminum undergoes a similar process. However, we actually need to really shove those electrons on there. Aluminum is very good at giving up electrons. So in this case, we take the aluminum ore, we generally process that into aluminum oxide, and then we melt it. We actually melt the aluminum, or the aluminum oxide, I should say. Then, using giant graphite electrodes, so this is going to make a ton of carbon dioxide, unfortunately, in this process. We run a high amount of electric current through the molten aluminum oxide. This forms molten aluminum metal. Now, interestingly enough, the melting point of the aluminum oxide is much higher than that of the aluminum metal. So that metal is ridiculously hot. So if we want to recycle some aluminum, it's actually quite easy. You wash it, you chop it up, and you just dump it in there. There's a ton of latent heat in that aluminum, so you can recycle a lot of aluminum in there just by chucking it in. You got to cool it off one way or another. You might as well cool it off by dumping in scrap aluminum. Now you get the aluminum out. Now, one point I want to make about renewable resources. Some resources are just straight up not renewable. We won't be manufacturing any more coal anytime soon. Same goes for petroleum products. Also, same goes for helium. Helium is generated by the radioactive decay of certain isotopes. It collects in pockets quite often along with natural gas. But when it leaves the container, it gets into the atmosphere, but it doesn't have a helium cycle. There is none, because helium is very much more of a linear system where it is light enough that the Earth's gravity can't hold on to helium, and so it escapes out into space. So helium is by no means renewable. However, certain sources of material can be renewable on small scales, but we can use so much it can't be renewable. A classic case is going to be aquifers. Aquifers do refill over time, but they refill relatively slowly. So if we suck out a bunch of water for use of, say, farming, we can very easily remove more water at a much faster rate than what is being replenished. And so the aquifer, even though that is a renewable resource, at the rate that we are using it, it is not a renewable resource. Now, the reason I'm jumping into this idea of renewable resources is, one, I wanted to mention green chemistry, but I also wanted to discuss circular economies. And this is an idea of us trying to live within our Earth systems in a way that doesn't damage them, in a way that respects them a bit more. Partially to respect the fish and to be nice to the fish, but also we depend on the Earth, we depend on our environment, and if we trash the place, then that's going to affect us. So the idea here on a circular economy, and I'm going to put up an infographic. In a linear economy, you're going to take energy and material input, and you're going to use that to make stuff. So your feedstocks, and you're going to make your stuff. Then you're going to ship it to wherever it needs to go, and then users are going to use it. And then once they're done with it, they chuck it, and you have to dispose of the waste. Now, that's a linear one. You're taking raw resources and you're creating waste. If you've looked at our system, so most of them are circles. Most of them are very circular. You have a cycle. So if we could take our economic model and turn it into a cycle, even if it's at least in part, that's going to create less impact on our environment and be a much more sustainable. We're not going to be wrecking the place. We're not going to be making a mess that future generations are going to have to clean up. No one wants a burning river. So the thought is, at that disposal step, is there a way to go back? Well, the simple one is, actually, before we get to the disposal step, can we use something longer? Can we make materials that aren't inherently disposable, that don't wear out instantly, and you just keep wearing them? This also has a lot of economic benefits. This the old saying that, inflation has definitely hit. A $10 pair of shoes will wear out after the end of the year, and your feet will be wet, whereas a $100 pair of shoes will last a lifetime, and your feet will stay dry. So you spend less money on the good shoes. Now, of course, that's an old-time saying, and shoes cost a whole lot more than $100. Inflation happened, but you get the idea. Quality products that last a long time to get a lot of use can be both better for the environment and better for the users. Unfortunately, they have a higher upfront cost, and there are certain economic reasons for companies to not wish to produce those. They would really like you to keep buying the shoes over and over and over again. So if they could charge you $100 and you have to buy them every year, that would be great for them. Terrible for you and terrible for the environment. But if we can use our products longer, have things that don't just artificially go out of style and you have to get rid of them for no apparent reason. They're still perfectly good stuff. If we could keep using, say, timeless wardrobes or other resources that just keep using. So, first approach, the most environmentally friendly tool or the most environmentally friendly shirt you own is the one you already own. Okay, next up, disposal. Could we reuse it? Okay, maybe I don't have any more use for the item, but could I get this to somebody else? Back in the day, this was much bigger. We had a lot of garage sales. People would sell their old stuff. People would go buy the old stuff and reuse it. We've kind of fallen out of favor of doing that, but it is much better for the environment. Well, the best shirt for the environment I can buy is the one I'm owning already. The second best shirt would be some shirt that somebody else already owned. After that, could we do remanufacturing or refurbishment? And I'll add to this one upcycling, which I think qualifies under remanufacturing. Basically, take the material, it's no longer in a usable state, but either upgrade it or change it into a new product through a much more involved process. So not just like sewing a couple buttons on, but reworking the material. Back in the day when cloth cost a lot of money, you didn't waste cloth. Nowadays, the cloth is used up. Your shirt's got a hole in it, you throw the thing away, maybe it turns into a rag. But back in the day when cloth was a much more expensive commodity, hey, you got a flour bag, and that flour bag just turned into a dress. Oh, that dress is kind of worn out. Now it's starting to turn into a quilt or some other use. And it's going to have a whole life cycle through it as we keep using that same sheet of cloth over and over again. We've kind of gotten away from that. So if we can get back to that, that would be awesome. And then finally, could we recycle the thing? Can we break it down into raw resources and use it as a raw resource? Back in the day, you remember the whole triangle? We used to say this a lot more, but the three-arrowed recycling triangle stood for reduce, reuse, recycle. So try and get less stuff, reuse the stuff you had to start with, and then recycle what you had. Recycle was always the last resort. But this way, we're extracting less material from the environment. Let's look at two materials in which we buy, one of which on a regular basis, the other probably not. But one is a very circular economy and one has a very linear economy. Let's look at some of the reasons why. The first, let's look at gasoline. This is a very linear economy. You dig it out of the ground, you purify it, you stick it in your car, you burn it, it's gone. You shove the waste, the carbon dioxide, out the tailpipe. Gasoline's relatively easy to acquire. Fairly low cost of acquisition, albeit sometimes it doesn't feel like that. And it's very, very hard to recycle the gasoline. You can't really reuse it. And the carbon dioxide, I guess you can feed that to a plant, but And it's more of just going up in the atmosphere. Trying to do a circular economy here is going to be inherently very hard. Now let's look at another one. One that's almost perfectly circular economy, and that's going to be gold. So if you dig gold out of the ground, you can totally do that, but it's an absolute lot of work because there's not that much gold out there. And so it's very, very expensive to go get fresh gold. Now, if you've got gold, it's actually very easy to recycle it. Just heat it up, melt it down, boom, you got fresh gold. It's not like it wears out per se. Even if you got a bunch of little gold shavings, you kind of put them in the pile, heat them up. You don't even have to get them that hot. Gold has a fairly low melting point for a metal. And boom, you got yourself a gold nugget that you can work into a new piece of gold jewelry or something. As such, you have something that's very easy to recycle and very high initial cost. So the economics are very much on recycle that thing. Sell off the gold, recycle it, make something new from it. And we have a very nice circular economy for gold. Not perfectly circular, but highly circular. Okay, with that said, have a wonderful day, and I will see you in future videos.